Have you ever imagined a dinner party going so disastrously wrong that it grinds everything to a complete halt? Well, let's talk about a classic computer science puzzle that does just that. It's not just a quirky story, it actually reveals some really deep truths about how computers handle their most complex tasks. All right, so let's set the scene. This whole thought experiment was first dreamed up by the legendary computer scientist Edgar Dijkstra way back in 1965. And it starts simply enough. 5 thinkers, a quiet evening, and one single giant bowl of noodles. But you've probably guessed, this isn't really about dinner. This whole fable is a perfect analogy for one of the absolute trickiest problems in programming. How do you get multiple different processes to share resources without, bringing the whole system to a crushing halt? Okay, so the rules of the restaurant seem pretty simple, right? To eat from that big bowl of noodles, a philosopher needs 2 chopsticks, the one on their left and the one on the right. The real challenge is to design a set of instructions, an algorithm, that lets everybody eat without causing total chaos. And this is where it all clicks into place as a powerful analogy for computing. See the philosophers? They represent individual tasks or threads running in a program. The chopsticks are what we call locks. They're a way to control access. And that big bowl of noodles, that's the shared resource all the tasks need to use, like a file, a database, or even a network connection. So, what's the first way this whole dinner party can just totally fall apart? Well, it turns out the system can get really unfair, really fast, and that can lead to some very, very hungry philosophers. Just imagine 2 of our philosophers are simply faster, or maybe they have a higher priority. They could grab their chopsticks, eat, put them down, and then immediately pick them right back up again before anyone else even gets a chance. The other philosophers would just be stuck there, waiting forever for their turn. Basically, they'd be starving. Now, the good news is we can actually engineer our way out of this problem. We can force those faster tasks to take a little break every now and then. Or we can use this really clever technique called aging, which basically boosts the priority of any task that's been waiting too long. It's a way to make sure everyone eventually gets their turn at the table. Okay, so that's one problem. But what if everyone is, equally polite? What happens if they all have the same priority and they all follow the same simple, logical rules? I mean, on the surface, this looks like a totally reasonable way to do things. Everyone tries to grab their left chopstick first, then they grab their right. It's fair, it's consistent. What could possibly go wrong? Okay, let's play this out. Picture it. In one single perfectly synchronized moment, every single philosopher reaches out and grabs the chopstick to their left. Then, they all politely look to their right, ready to grab that second one. A total system freeze. That's what. Every philosopher is holding one chopstick, and they're all waiting for the chopstick that their neighbor is holding. And that neighbor? They're waiting for their neighbor. You see where this is going? It's a perfect circle of waiting. And now, nobody can move. And that perfect circle of waiting has a name. Programmers call it deadlock. It's basically starvation, but for the entire system. Nobody was being greedy, but because they all followed the same simple logical rules at the same time, the whole process has ground to a permanent, irreversible halt. So, right, how do we fix this mess? How do we change the rules of the restaurant to break the stalemate and finally get everyone fed? Okay, so one idea is to introduce timeouts. If a philosopher waits too long for that second chopstick, they just give up, put the first one down, and try again later. And this can break the deadlock. But it can also introduce a new, kind of hilarious, but also really frustrating problem called live lock. Imagine everyone times out at the exact same moment, puts their chopstick down, and then tries to pick it up again at the exact same time, over and over, forever. The system looks busy, but absolutely no one is eating. So timeouts are tricky. A much better, more solid solution, one that Dijkstra himself came up with, is to break the symmetry of the problem. We just have to stop everyone from doing the exact same thing at the exact same time. So instead of thinking left and right, we just number the chopsticks, 1 through 5. Now the rule is simple. You must always pick up the lower numbered chopstick available to you first. And bam! That one little change makes that circular waiting pattern literally impossible. Someone will always be able to grab both of their chopsticks and eat, which breaks the chain for everyone else. All right, our last approach is basically to bring in a manager. Think of it as hiring a waiter for the restaurant. With a central arbitrator, our waiter, in charge, philosophers can't just grab chopsticks whenever they want. They have to ask for permission. The waiter makes sure that only one person gets to even try to eat at a time. This is a guaranteed, foolproof way to prevent deadlock. But, and this is a big but, it totally kills parallelism. It's the safest option, for sure, but it's also the slowest. It's a classic trade-off between absolute safety and system performance. So, after all that, why should you care about this weird philosophical puzzle? Well, because this isn't just a thought experiment. These are the exact kinds of problems that software engineers are wrestling with every single day. And getting this stuff wrong has huge consequences. A bug very similar to this, known as priority inversion, caused a series of complete system crashes on the Mars Pathfinder rover. The entire mission was almost lost until a team of brilliant engineers on Earth managed to debug and fix it from millions of miles away. Look, from the operating system on your laptop to the web servers that run the entire internet, and even the software that guides spacecraft through the cosmos, managing how all these different processes share resources is absolutely critical. Getting these rules right is what makes our modern world, well, work. And that's really the big takeaway here, isn't it? It's this powerful reminder that in our incredibly complex, interconnected world, the most catastrophic failures often don't come from one big, obvious mistake. No, they emerge from these simple, seemingly logical interactions between all the individual parts.